EMP strike scenario, the secret Faraday protection. They don't want you to know. Imagine waking up to a world where the lights never come back on. Your phone is silent, your vehicle refuses to start, ATMs display nothing, radio stations vanish, and the invisible digital infrastructure supporting modern civilization appears to have disappeared in a single instant. An electromagnetic pulse, commonly known as an EMP, is often portrayed as a mysterious force capable of destroying everything electronic overnight. But the real danger is both more complicated and more unsettling. The greatest threat is not the pulse itself, it is widespread misunderstanding. People often prepare for dramatic explosions while ignoring the quiet engineering principles that determine whether critical equipment survives or fails. Understanding those principles is not simply an exercise in physics, it is a matter of resilience. Every electrical conductor, every cable, every antenna, and every circuit becomes part of an invisible experiment conducted at the speed of light. Whether devices continue functioning depends less on luck than on the paths through which electromagnetic energy can travel. An EMP is not a single phenomenon, but a combination of rapidly changing electromagnetic fields. These changing fields induce electrical currents in conductive materials according to well-established laws of electromagnetism described by Faraday and Maxwell more than a century ago. Contrary to popular belief, electromagnetic energy does not seek out electronics with malicious precision. It follows physical rules. Long conductors collect more induced energy than short ones. Poorly protected systems connected to extensive wiring networks are generally more vulnerable than isolated devices. Massive electrical grids, communication cables, and transmission infrastructure present ideal pathways for damaging surges because they act like enormous receiving antennas. This distinction is frequently overlooked. Many people assume a disconnected flashlight is as vulnerable as a citywide power transformer, yet the difference in scale fundamentally changes the amount of energy that can be coupled into each system. Another common misunderstanding is that every electronic device would instantly fail during every possible EMP event. Scientific testing and engineering analysis suggest a more nuanced reality. Device vulnerability depends on pulse strength, orientation, shielding, grounding characteristics, internal design, cable attachment, semiconductor tolerances, and distance from the source. Some equipment may continue operating with no noticeable damage. Others could suffer temporary malfunctions before recovering. Still, others could experience permanent component failure because induced voltages exceed the breakdown limits of delicate semiconductor junctions measured in nanometers. The outcome is not determined by fear, but by physics. This variability explains why engineers approach electromagnetic compatibility through probability, testing, and layered protection rather than absolute predictions. Hidden beneath sensational headlines is one of the oldest and most reliable protective concepts in electrical engineering, the Faraday enclosure. Many people imagine an expensive military bunker lined with exotic materials, but the underlying science is remarkably straightforward. A properly constructed conductive enclosure redistributes electrical charge across its outer surface, reducing electromagnetic fields inside the protected volume. The effectiveness depends not on magical metals, but on electrical continuity. Tiny gaps, poorly connected seams, unshielded openings, and conductive paths entering the enclosure can dramatically reduce performance, particularly at higher frequencies where even small discontinuities behave like antennas. This is the overlooked detail. Protection is often determined not by the thickness of the metal, but by the quality of its electrical connections. Evidence from electromagnetic compatibility laboratories demonstrates that shielding effectiveness is measurable, repeatable, and governed by established engineering standards. Facilities test equipment against intense electromagnetic fields to evaluate resilience in aviation, telecommunications, healthcare, industrial automation, and defense applications. Shielded rooms, conductive gaskets, filtered cable penetrations, and carefully bonded joints are standard engineering solutions, not mysterious technologies. These methods reduce field penetration by many orders of magnitude when correctly designed. The principle is the same whether protecting sophisticated laboratory instruments or preserving a small emergency communication device inside a well-constructed conductive container. The survival implications extend far beyond preserving gadgets. Reliable communication after widespread infrastructure disruption determines access to weather information, emergency coordination,